Hello everyone, my name is Maria del Rayo Morales Diaz. I'm a student of master degree in semiconductor devices at Centro de Investigaciones en Dispositivos Semiconductores in the Benemérita Universidad Autónoma de Puebla, and today I'm going to present my work titulated Modeling and Simulation of Transparent Solar Cells based on the heterojunction of titanium oxide as N material and nickel oxide as P material of the union. Well, nowadays there's a great need to make use of renewable sources for energy production, since the current environmental situation requires responsible and conscious actions that allow satisfying the needs of the population without continuing affecting the planet. Well, this is why the technology that uses solar energy as an energy source has been widely studied, because solar cell energy is considered an inexhaustible resource. Well, the TCOs or the transparent metal oxide that are the materials for the heterojunction that will be simulated in the present work offer a great promise as an affordable, environmentally friendly, sustainable, and viable energy solution. Well, it has actually been reported that the dioxide, titanium, and nickel oxide has been used to manufacture a solar cell, obtaining an efficiency of approximately 2.3% in the device. Well, for making these simulations, we will be using the SCAPS or the Solar Cell Capacitance Simulator because, well, it has been implemented in the solar cell research, so it has been given good results as simulation stuff. Well, for making the simulations, it's important to give some properties of the materials, as we can see here in this table, where we have the material properties for simulation in SCAPS 1D, where we can find the band gap, the electron affinity, the dielectric permittivity, the effective density of states in the conduction band, the effective density of states in the valence bands, the electron and hole mobility, as well as the shallow uniform donor density and the shallow uniform acceptor density. Well, these two last parameters or properties are important because it is something that we can see that if it's N material, we have the donor density of states, but we have P material where we have an acceptor density. Well, in these parameters, we can see some things that are very curious about the materials. For example, the band gap. Well, normally, the band gap of the N materials of the union must be bigger than the P, that the value of the P material of the band gap material. Well, here we don't have this case. We have a value that it's minor than in the P region. Something that also we have to notice here is that the shallow uniform donor density it's minor than the shallow uniform acceptor density, which is also not so common. But for observing this in a better way, we have a resource, a tool that is very useful to analyze what is happening in the third junction. That is called energy band diagram. Well, for this energy band diagram, well, were made several calculations according with the properties of the materials. Um, but basically here we can see, the principal resource. For example, the potential in the N part is greater than in the P part. So we can infer from this that the formation of the electric fields predominates in the in region of the junction. Well, another notable feature is that the depletion region in the N region of the material is much larger than in that on the P side. Um, well, according with the results and in relation with the properties of the materials, there are two possible forms of illumination of the heterojunction. Well, the first having the N layer as the window layer and the P layer as absorber layer, which can be the normal form of illumination of the solar cell, or by the other hand, having as a window layer the p layer and as absorbent layer the n layer. Well, according with the properties of the materials, well, this can result more useful. Well, what is happening in the simulation? Well, according with the results, we have here the JV characteristic curve for a solar cell illuminated from the ends part of the junction. Well, here we can see that several simulations were made to find the best thickness of the window and the absorber layer. So we can find that the window layer thickness is 275 nanometers, and the absorber layer thickness is 1400 nanometers. That is made of nickel oxide. Well, here we can see that the result of the efficiency is 3.23%. That it's near to the one that was obtained from the manufacturer solar cell that was in 2.3%. But something that is important to observe is the relationship of the fill factor, that it's 58.01%. We can infer from here that the voltage and the current actually has not the best relation for the parameters that they are resulting for the simulation. When we have the simulation and we already find the thickness of both layers, well, we have to find the contacts that can work for make this simulation to work better. And for this, we have a back contact made of iron and a front contact made of aluminum, which actually increase the efficiency of the system from 3.23% to 3.76%. So actually it can be useful to have these materials in the contacts, but for sure the efficiency is not like very important. It's not an impressive result. But what happened when we illuminate the solar cell from the other side? When you have the JV characteristic curve for a solar cell illuminated from the P part of the junction. As we can see here, well, we have a result of 8.58% of efficiency and a 67.44% for the fill factor. So the relationship between the voltage and the current is actually better than when we illuminated the solar cell from the inside of the junction. And what happened when we find here that the window layer thickness that it's now the nickel oxide, because this is the material from where the light will be induced, it's 250 nanometers, and the absorber layer thickness that it's now related with the titanium dioxide, it's 1800 nanometers. So there is a better work for this kind of solar cell according with the simulation. And when we find the materials for in the back and the front contact, well, we actually have the same materials for both contacts, aluminum and iron, but the increases of the efficiency, it's better because we have 8.58%, and now we have an 8.64%. That is much bigger than when we illuminated the solar cell from the inside. So here we have a comparative chart with both results of the illumination of the solar cells. In color green, we have the illumination from the end part of the region, and in color blue we have the illumination from the p-bar of the junction with the ideal characteristics and the contact materials. So from this graph, we can see that actually the efficient increase in a very good way for the P illuminated solar cell. So we can see here in the results of numeric results that the efficiency from the solar cell that was illuminated from the N side almost was duplicated by the solar cell was illuminated from the P side of the junction. So now we have the same materials from the context and a very similar thicknesses for the window and the absorber layer. So it can be inferred that when we illuminate the solar cell from the P side of the region, well, actually the solar cell will work as a normal solar cell, because in this way it will have the best properties for working. So in conclusion, well, for a solar cell illuminator from the inside of the junction, the ideal thickness are found to be 275 nanometers for the window layer and 1,400 nanometers for the absorber layer. For a solar cell illuminator from the P side of the junction, well, ideal thicknesses are found to be 250 nanometers for the window layer and 1,800 nanometers for a sublayer. So for both types of lighting, it was found that the contact materials are iron and aluminum. Something important here that is when we made this simulation was found that in both cases, as the temperature increases, the efficiency and the fill factor decrease. So this is a normal comportment, or this is a normal behavior of a solar cell. So it indicates that in both cases, the solar cell is working okay, is working good. So we have a very tangible solar cell that is illuminated from the P side. Well, an efficiency of 3.46% was obtained for a solar cell illuminator from the N part of junction with ideal operating characteristics, while for the solar cell illuminator from the P part of the junction with ideal operating characteristics, we have an efficiency of 8.64%. Well, therefore, it can be concluded that for this ether structure, it is better to illuminate the cell from the P part of the junction. So thank you very much for your attention.